This demonstration of the ACE in-memory embedded global cache involves 4 independent integration servers that are all running on the same local laptop machine. In server 1 we have a flow to write to the cache, and server 4 will have a flow to read from the cache. Cache replication is happening between the different servers. You can see the pairs of yellow lines and green lines to show that process. Each separate server has a different replication listener defined, running on different ports. Switching to the integration toolkit, we can see each of those servers is already started. The server configuration YAML documents have already been defined, and we have already created a couple of message flows that will be used to interact with the cache. Starting with a writing flow, we have a Java compute node which uses the same interaction model that was introduced in the old WebSphere Extreme Scale global cache feature. In the highlighted text, we're creating a person map, which is the name of the MB global map object, and inserting into that person map object a person's name and age, which has been parsed in from the input message, which is triggering the message flow. In the cache read flow, we then have a graphical data map which attempts to retrieve the value from the cache. When we retrieve the value, we need to have a key for that value. That's the name of the person in this example. The assigned statement in the map is defining the name of the MB global map objects from which we want to retrieve the information. In this example, person map. So with these simple message flows, we've got a way of writing to one or more server caches and reading from one or more server caches. We can use the IBM int display cache command in order to see the current status of the various servers in our architecture. Currently there are 0 keys defined within the person map object, both within server 4, which is the first command, also within server 1, which is the second command, and also inside server 2, which is the third command, 0 keys inside each of these. We don't need to bother looking at server 3, but if we were to bother to do so, we would find that there's no data inside there as well. We're now going to deploy the write cache flow to server 1. Once we've done this deployment, we can parse in some data about Ben in order to inject Ben's age into the cache. That is then going to replicate as a write to not just server 1, but also server 2 and server 3. We can see the JSON data structure here says that Ben is age 21. Always good to know, and the response message that comes back tells us that the cache has been successfully updated courtesy of that Java compute node logic that we were looking at just a moment ago. Returning to the command line, we can run the same query against server 1, and we now observe that the person map contains 1 key, so we've successfully injected the data into the local cache owned by server 1. We can also check out servers 2 and 3, and this will prove that the replication that we are aiming to happen has also successfully completed. Both server 2 and server 3 have 1 key inside their maps. Server 4 at this stage does not have any information inside person map, and that is how we're going to deal with the reading of the data in just a moment's time. We'll see that the read cache is working. So we're now deploying the read flow that's going into server 4, and we're going to send a query into that flow with the name of the person, Ben in this example, to figure out what Ben's age is by doing a query on the cache. So there's a name in the input structure. We can check out the reply, and we've discovered that sure enough, Ben is age 21, so the lookup in the cache has worked successfully. If we repeat the administration command, we can find out that now that person map object is inside server 4, sure enough it contains 1 key, whereas it had 0 keys before. And this proves that replicated reads are happening successfully too across the various server infrastructure that we've defined in our example. We're about to send in some more data for Sanjay, but before doing so we're going to stop server 3. This shows that when doing writes into a cache, we have a list of potential servers that we would want to append with that data. In some circumstances, maybe one or other of those servers might be unavailable. In this case, we've deliberately stopped server 3, and if we go back to the command line, we can prove by running the IBM int display cache command that server 3 is definitely currently out of service with the error response that comes back from the IBM int command. Leaving server 3 in a stopped position, we can then inject data into the cache write flow, but this time for Sanjay, who's age 25 by the way, rather than Ben, which was previously already in the cache. That cache update has still been successful, and we can repeat the read operation against Sanjay, and due to server 2 still being online, the replicated writes and the replicated reads have still successfully replied with Sanjay's age. So to conclude our demonstration, we can then go to the display cache command and show that now server 4 contains both those keys, so successfully showing the replication of data between multiple servers in a cache topology. This demonstration of the new ACE Toolkit Container Explorer actually starts live inside the Red Hat OpenShift console. You can see on this particular Red Hat cluster that we've already got the IBM App Connect operator installed. Underneath this operator, we have an example of an App Connect dashboard that has already been created. Several artifacts have been deployed into it, in fact. You can see on the panel of the properties an API, and this API is being copied into my buffer in order for us to use it in a moment when we get into the toolkit. If we go off and explore the dashboard within our web browser session, we can start to see the kind of information that we might expect in a moment when we start examining the Container Explorer itself. So inside the web browser here, I can see I've got several started integration runtimes. In this particular one, I have an application called Backend Application with a couple of flows deployed. And we can also navigate up and investigate another one of the servers. If I drop into the coordinated request reply server, I have an application here too, with again a couple of message flows. These flows may be in a started state, things may be stopped. I have a variety of different functions here. I can also navigate to the bar files that have been uploaded to the dashboard previously. I've got 5 separate bar files here. A couple of them are not deployed anywhere, and the echo deploy bar file is actually being used by 4 separate integration runtimes currently. So we've got a range of bar files that are already in use. Turning our attention to the toolkit, we can now see the new Container Explorer, which enables us to add a connection to an existing dashboard. I can paste the URL from my buffer that connects us to that existing dashboard situation. I can provide a username and password, but I'm just going to cancel out of that dialog and return to the existing connection which I previously used. I'm going to right-click that and connect to the runtime system. You can see the hierarchy beneath each dashboard is split into 2 separate sections, one containing bar files and another one integration runtimes. I can select an individual integration runtime and choose to expand it to see more information about what has previously been deployed to it. You can see the status gradually get updated, and as we make those API calls, we then get responses back that show the various icons of the policy project and the deployed application. I can pick on a different integration runtime and also see information about that one. If I just click on an individual integration runtime, I can also get a view of the number of replicas that are currently running and when they were started. That kind of basic information. When I go to the bar file section of the hierarchy, I can choose to upload a bar file from my local Eclipse workspace and have that added to the dashboard. I'm going to select one here that interacts with Kafka, and you can see the reply messages come back to say that it has been successfully uploaded, and then the hierarchy has been updated. And we can now see the Kafka bar file in the left-hand panel. Flipping back into the web browser session and the dashboard there, we can see the same information has now been reflected in the bar files section. So previously we had 5 bar files and now we have 6. Now this bar file has currently only been uploaded. It has not yet been used when starting up an integration runtime. I have other features here to update the bar file or delete the bar file from the system altogether. We can also make further updates to the integration runtimes themselves directly. If I select IR03 Quick Start and query its details, when the dialog responds in the bottom right corner, you'll see some high-level properties that we were referring to earlier about that particular IR. In this case, it already has the Echo application deployed to it. We can choose to remove the bar file, or in this example, we're going to add some extra content. From the Add Bar dialog, we can see a list of all of the current bar files that are available to us. We're going to choose to add mydeploy.bar. The warning here is saying that I've got an option to wait for the integration runtime to be updated, and then my visuals will be shown updated and refreshed in the toolkit. This can sometimes take a few seconds. The reconciliation process of applying new bar content into the integration runtime can sometimes take a while to complete. So having agreed to wait, you'll notice that it's getting back the details, and once that update has happened, you'll notice within the IR03 area, we'll now have the presence of the extra application. My new app has now been deployed too. So welcome to this demonstration all about Kafka nodes as part of Designer message flows. We'll come to the Designer in a moment, but to begin with we find ourselves in the Red Hat OpenShift console, and we're going to begin by looking at an IBM Event Streams implementation which we prepared ready for this demonstration. Event Streams is an example of a Kafka provider, and we can see here that we already have installed the operator. We've already created an instance of Event Streams, and we have an administration UI that can be used to configure various things like the topics that are available. If we go to the Topics tab, we're going to create a couple of topics that are going to be used by our demonstration. We'll call the first one Ben Input Topic, and when we go to the next panel, we'll be faced with further choices about how many replicas we'd like for the topic, how many partitions we'd like. We're going to create a second topic now, which is called Ben Output Topic. The purpose of this topic is, unsurprisingly, going to be the output from our Designer message flow. We can choose the message retention, we can choose the replication factor, and then when we hit the end of that wizard, we've now got the two topics that are already created for us. We're now going to go to the Designer. This is running in a web browser as part of my on-premise ACE installation, and I'm going to create an event-driven flow that I will choose to give a new name, My Kafka Demo. We can now add additional nodes into the flow. I've already configured this system with the properties required to authenticate with Kafka. You can see I've already got an account set up, so I'm simply going to choose that this particular flow should be triggered when a new message is written to the topic, and it's going to be on the Ben Input topic that we just created. I'm choosing to take messages from the latest of the message offsets. This is giving us the latest data. I'm then going to add a second node into my flow. Just for the sake of something to be a little bit different, I'm going to add a logging node here whose purpose is to inject an entry into our local log file. When we're actually invoking the flow, we'll then be able to see evidence that it has been successfully invoked and that the message has come through the Kafka input. You can see that we can type a free-form message here, so the message detail will be "Message has been retrieved from Kafka." The final node that we're going to place in our flow is the opposite to the Kafka request. This one is going to be an outbound Kafka message that we're going to choose to write to a topic. We're choosing the Send Message option from the drop-down. We're going to select Ben Output Topic, and then we have some options to include various inputs from the earlier nodes in the flow. In this case, I'm just copying across the payload of the Kafka message that we retrieved from the first topic. So pretty boring in terms of transformation, but this will show the process of moving the messages around. We're now going to place the flow into a testing mode. You can see in the top right corner that this has now been confirmed. The flow is running and it's ready to be tested. In order to send data into the flow, we're going to take this opportunity to demonstrate the ACE Toolkit as a means of just injecting some data. We're going to drive that from an HTTP input, and then we're going to set up the structure of the data that will be sent in using a JSON message. And we're going to examine here the age of the person that has been described, and use that age to deduce which football team is their favourite football team to support. As we all know, this is all based on how old people are and which teams are successful at the time. The next node in the flow is the Kafka producer node that's been configured with a topic name and also a Kafka policy. The policy extracts various important pieces of information about how to connect to the Kafka system. You can see the first of these properties is the Bootstrap service property. We've also defined that we'll use SASL SSL when authenticating with the system. We have a trust store set up. We also require a security identity that will enable us to connect into that trust store and extract the information that we need from the certificate that's been presented from the Kafka system. So with these settings already created, we've got the integration server already running. We're deploying the Kafka policy that uses the settings that are already in the credential vault, and then we'll be in a position to start up the message flow. By placing it into recording mode, we can then inject the HTTP data that we discussed previously. This is a very simple JSON message which will describe the person. It will start off with a name and an age. I'm Ben, and unfortunately I'm age 46. When I receive the response back, you'll find that my favourite team is Tottenham Hotspur. What's actually happened in order to get all the way back to that HTTP reply node? Well, the first thing that happened is that we used the Kafka node to invoke the designer flow. We can check that that's actually happened by going to the log that we were referring to earlier, the activity log, and doing a refresh. We can see that the message has been retrieved from Kafka. So the ACE Toolkit flow was able to successfully send a message into event streams, which then triggered the designer flow. And if we go to the output topic, we should be able to see that the message has landed all the way through both systems, and sure enough, there it is. Ben, age 46, whose favourite team is Tottenham Hotspur. This example will demonstrate the new retry settings that we have on the HTTPRequest node in ACE 13030. We'll be using two different local test integration servers. These are independent integration servers and they've already been started. We'll be interacting with two different message flows, one deployed to each server. The demo HTTP requester flow is driven from an HTTP input that then seeks to invoke an HTTP request node, whose purpose is to call the second message flow deployed to our second server. To begin with, the HTTP request node has a retry mechanism of no retry set. This is the standard settings that were there prior to this new feature being implemented. We're going to deploy this message flow, and when we invoke it by sending in some test data, a simple message that just says hello, we will find that the HTTP request node is unable to immediately return to us in the requesting flow. This is unsurprising, given that the flow that it's attempting to invoke is currently stopped. After a few seconds, we do get a reply message back, but when we exit the dialog, you'll notice that this is courtesy of the failure terminal having been invoked from the HTTP request node. Looking at the detail of the message assembly, if we expand the exception list, we can get further feedback about what is it that caused the recoverable exception. Expanding the various levels show that this was a socket exception that occurred, and we have some more detailed error codes. If we expand the inserts, we can see that this was a situation with WSAE con refused. This particular socket exception can be picked up by the HTTP request node, and as a result we can then enter into a loop of some retries. If we remove that flow from recording, we can actually start up the back-end message flow and look at the flow in a successful course of action. If we again redeploy the message flow and test it out, we'll be able to send in the same test data, but this time with the back-end message flow started. We'll get an immediate response, and leaving the testing dialog, we can see that it's now come out down the out terminal of the HTTP request node. So this shows that in successful operation, there is no problem. If again we remove those flows in their current state and return test server 2's message flow into a stopped status, we can then repeat the experiment. But this time we're going to use some short retry settings, which will attempt 10 times over to use a retry interval of 5 seconds. On the detailed HTTP retry conditions, you can see that we can check for econ refused. If we redeploy this message flow with the new settings, we can then see the impact when we invoke the flow with the same data that we ran through before. With the flow in the testing mode, we will inject the simple hello message, and this time when we hit the HTTP request node, the message flow will be unable to return to us immediately, but it will enter into a retry loop to attempt further pings to the back-end flow. You can see here that no response has come back. If we exit the testing dialog, currently the blue line has got as far as the HTTP request node. I can actually go to test server 2 and start up the back-end message flow. And having done so, if we examine the path that has been followed by the original requesting flow, we will now see that it has been released, the response has come back, and we've successfully made it to the HTTP reply. So, the retries have been a success. This demonstration will show the new feature on the Callable flow nodes for checking supported message domains. On this Callable input node, you can see that we have pre-configured the Supported Domains tab with a couple of entries denoting that XML NSC and JSON are supported domains, and we've chosen to check inbound messages to see whether they match those domains. The next node in our example flow does routing based on the properties header of the message down one of two different branches. In this first branch, we know that the inbound data is JSON, and we'll be doing a graphical data map to convert the message to XML, having uppercased the value of one of the fields. The other route through the flow is receiving an XML input and mapping to JSON. It's going the other way around, and likewise doing the uppercasing of a single field. Before we start examining the client message flow, we're just going to deploy the artifacts that we've seen so far. I'm deploying a shared library that contains the XML schema that we were using, and we're also deploying the demo Callable flow application that hosts the message flows that we were just looking at. Having deployed these artifacts, we can then open up the administration web UI in order to find out more information about the metadata that we store about those deployed flows. If we go to the Resource Managers tab and then look at the Callable Flow Manager, we can then look at some detailed information that includes info about the style of messages or message domains that are expected to be received by this message flow. This is a queryable property which can also be sent off to our switch server in the circumstances where the callable flows are running on different platforms, and it ends up being a nice way that we can discover information about the deployed flows. We're now looking at a second message flow whose purpose is to invoke the first one using a Callable flow invoke node. There are actually 3 different entry points into this flow, each using different message domains. One of them is binary large objects, blob domain, one is our XML structure, and the third is our JSON structure. What we're now going to do is deploy this message flow and then use those HTTP input nodes to try sending in different pieces of data and look at the responses that we get back from the callable flow which is being invoked. In the first case, I'm sending in a piece of XML. This is conformant, and we know it's one of these supportive message domains as well. So when we receive the response back, you'll see it's been edited, transformed into a JSON structure with an uppercase field applied to the favorite team property. If we look at the recorded message assembly, we can see that the properties field has carried the name of the shared library where the schema was sent through. And that is what caused the data to be sent in the direction that it was. We can repeat the test using an input in JSON format as well. In this case, again, everything has been successful. We've gone through the callable flow invoke. The properties header of the message assembly shows that we had the person JSON values set into the message set field. And then we reacted accordingly when it reached the callable flow. Now, things get interesting. When we send in this third example, we've sent data in over the binary large object domain, which is not one of the supported domains on the callable input node. You can see that we've had an exception passed back to the invoking flow that describes this problem. And this demonstrates that we're successfully checking inbound messages in the callable input node to see whether they match the supported message domains. The App Connect Professional Studio helps users author orchestrations which are grouped together into projects. In the example here, we're concentrating on an integration task that receives JSON data over HTTP, parses that structure, and then uses an if block to choose between 2 alternate logging paths before replying back to the initial requesting client. A simple log entry will record whether the if branch was invoked or the else branch was invoked based upon the value of a country field in the inbound data. Once the orchestration has been started, as shown on the screen, we can then use the Studio's built-in testing utility to try out the orchestration. Once JSON data has been submitted to the inbound HTTP URL, each stage of the orchestration's behavior is displayed in the top right corner. Expanding the sections of the hierarchy will show details of each of the completed steps, which demonstrate that in this example the main if branch evaluated to true because the country field carried the value GB. We can also observe that the final output from the orchestration is the same data structure that was sent in at the beginning. The next stage of our conversion demo is to explore a plugin archive file containing all the details of the orchestrations in the current project. We're saving this PAR file to a directory on the local disk system, which will then be imported into the App Connect Enterprise Toolkit. Switching to the App Connect Enterprise Toolkit, we will begin by exploring the new conversion option from the File Import menu. This new capability lets users import an App Connect Professional PAR file for conversion. You can browse to the local file system location where we saved the exported PAR file from the studio just a moment ago. When we click the Finish button, all the orchestrations located in the PAR file are converted into message flows grouped into an application, which in this example is named Demo. On the left-hand side, under the Application Development workspace, there is a .messageflow file open in the editor, showing the message flow that mirrors the structure of the original ACP orchestration. There are some nodes that are displayed, and the red icons indicate that a manual configuration is required to finalize the flow. To perform the manual configuration, we can see that there is an auto-generated documentation showing the required manual configuration. There is a configuration properties file generated which has all the configuration properties and their values used by the ACP project. There is a task tab. In this panel, it lists all of the nodes that require attention. Each is clearly identified with the corresponding to-do. Clicking on the task from the list highlights the corresponding node in the message flow. This makes it easy for the user to navigate between the pending tasks and complete the configuration step by step. In the lower Properties tab, under Description, there is a to-do message left by the conversion tool. By clicking on Open Link, you are taken directly to the relevant section in the documentation, which makes it easy for the user to configure the particular node as the instructions are provided in the documentation. Our recording will rejoin the toolkit once all the tasks from the task lists are addressed and configured accordingly. Our converted message flow is now ready to use. The input URL is configured and the root node expression provides the same capability as the if activity in the original orchestration. The two log nodes have messages configured showing which of the logic branches has been invoked. We'll now use the Toolkit Flow Exerciser to deploy and try out the message flow in the local server. The same JSON data structure which we used for testing in the studio is repeated here. The country field will determine which branch of logic is executed. The display also shows that the flow echoes back to the requesting client the same data structure which triggered the flow. Closing the display reveals a blue line showing the direction in which data has travelled through the flow, and clicking on a wire of the flow shows the data structure at that stage. Exiting the test mode, we can also now launch the App Connect Enterprise Administration UI. This web browser-based experience shows deployed applications, and drilling into an application reveals the message flow, including an activity log view that shows the log entry which the flow has recorded. This concludes our demonstration, which has shown how to easily convert App Connect Professional orchestrations into App Connect Enterprise message flows.